Well, good morning, everyone. Thank you for being here on time. Dr. Page is out of town. He asked me to introduce our presenter today, and it is indeed my distinct pleasure to introduce Dr. Bruce Kaplan. Dr. Kaplan was born and raised in New York, where he completed his Bachelor's of Science at Adelphi University. His medical degree was received from Columbia. He completed his residency at Mount Sinai and his nephrology fellowship at Stony Brook University. He came to the Midwest, where he completed his clinical pharmacology fellowship at Northwestern, where he started his first position as an assistant professor of medicine at the same institution. And then he rose through the ranks to the full rank of a full professor, working at some of the key institutions in the country, including the University of Michigan, University of Florida, Gainesville, University of Arizona, Mayo Clinic, Scottsdale, and he is currently the Vice President of Strategic Affairs and Transplant Services at Baylor, where they are working on an integration process just a bit more complicated than the one we have gone through. Dr. Kaplan has written more than 300 papers and book chapters. He has an H index of 65 for the residents and fellows. That means that he has 65 papers at least that have been cited 65 times. That is really high. He has been the deputy editor of one of the key journals in our field, the American Journal of Transplantation, and he was just asked to become the executive editor of another key journal, that's the Journal of Transplantation. Dr. Kaplan has received a number of NIH and foundation grants in the field of transplantation, and specifically biomarkers, immunosuppressive agents, tolerance, and so forth. And most importantly, Bruce has been a great mentor to me, and a great friend, and a great human being, and I am delighted having him here today to talk to us about biomarkers in kidney transplantation. Please join me to welcome Dr. Kaplan.
I just really want to thank Aji for that way too kind introduction. It's a long time. I want to thank Aji for years of friendship. I knew Aji when he was that tall. And he's not here, and that just goes to show you how you... So everybody's... I got to erase this after today. For the last 24 years, and I hate to say that, I hate to think it's been 24 years since I began. You know when they ask you the key question about the code, your secret codes of every computer and how to unlock it, your secret question, they ask you who your best friend is. And for 24 years, it's never always been the same one. It's been Dixon Kaufman, who is a transplant surgeon here, who's been an incredible colleague, friend, mentor. Can't describe the connections. And more than anything else, more than any number of papers, positions, the things I cherish most are the people you meet along the way. And of the people I've met along the way, I cherish the people, Dr. Janway, Dr. Kaufman, more than almost any others around the country. And so it's, for any other reason, it's a real privilege to be here. Aside from this is a great school. I guess there's a template of a CME. I don't have, unfortunately, any financial disclosures. And we will not be talking about any unlabeled or unapproved use of anything. We'll just be talking about no unlabeled, unapproved ideas and talks. So the topic is, why don't biomarkers work in transplant yet, or why we? But the other title was, this build was, you can't fool Mother Nature. So I don't want to get caught up in the weeds of a lot of all the chemicals I'm going to talk about, the chemokines, the transcripts, all that kind of transplant-y talk. I think the key thing is, if you take anything from this talk, which I hope one or two things come through, is that a lot of what we think to be true, it doesn't always bear out to be true. And then sometimes the questions we ask, we answer, but they weren't the right questions. And the last thing is that we do live in this incredible age of technology. But we haven't kept up with the mathematics and the ability to do and make sense of the millions of molecules we come out with every day. And lastly, that if you think about some of the great projects that have been done over the years, some of the things have required a group of people from different disciplines to solve the problem. If you think about the Manhattan Project, you had physicists, you had engineers, you had mathematicians, you had carpenters and carpenters' wives, and everybody involved. And I think in terms of complex systems like the immune system, to kind of figure it out, I think we're going to need help from all the disciplines, because it involves the very nature of who we are. Think about a transplant and think about how it's really about the fundamental question of self and non-self, and how we deal with the outside world, and how we perceive something to be a danger or not a danger. And then you can start realizing how complex it is. So we'll try to make it simple, but I don't know how I'll try to navigate trying to make a complex system simple, but hopefully the message is simple. I do other stuff, but I don't have any financial interest. Please, write letters to them or something. But I'm an advisor at Transplant Genomics Incorporated, another genomics company, Generic Incorporated, funding for NIH funding for another biomarker study, CTOT-8, and part of the Genome Canada Consortium, or so-called Precision Medicine and Transplant. And all of them would be really upset at this talk. So for the search for predictors or biomarkers are the really wrong term. Biomarkers are anything that's biologic that markers for something. So when I'm talking about biomarker, I'm talking about predictive or prognostic biomarkers. And I'll go through those definitions in a second. So that search for something that could predict ahead of time acute rejection has been ongoing now for well over 20 years. Really 30 years. And the mystery is, 30 years ago, we found it. And then since then, we've had at least 50 multi-center NIH-funded studies looking for a new one. And each one shows the same result, no matter what molecule you use. I'll show that in a second. And you know what? We don't use a single one. So I'll try to walk you through all of that. So I'm just going to go back to since 1999. In 1999, I'll later go through this. 1999 was the first study. Came out in Noonan Journal of Medicine from the Cornell group, of looking at very simple, that urinary cytotoxic lymphocyte products could accurately predict rejection before it occurred 90% of the time. A biopsy is only right 50% of the time. That's incredible. And since that time, we spent over $1 billion searching for new biomarkers. And I'll go through those in a second. So let's just define biomarkers. So biomarkers are classically, when we talk about them, we tend to talk about them as predictive, prognostic, or surrogate. And then we talk in terms of sensitivity, specificity, negative and positive predictive values. And I want to hone in on the negative and positive predictive values because that's going to be a big part of our talk. So sensitivity and specificity are the intrinsic properties of a test. But negative and positive predictive values are Bayesian ideas. They tell you when you get a test back, what's the chance of that being a truly positive or truly negative test? And that is very dependent on the prevalence in the population. So when you deal with very low frequency events, it's almost impossible to get a high positive predictive value. One of the trick questions people will ask you, and recently Richard Thaler won the Nobel Prize in Economics, but it's a classic question is, what would you do? Someone with low risk for HIV, and I tell you an HIV test is 99% accurate, and you find out someone has a positive HIV test. What's the chance that they have HIV? Well, if you just go through the little bit of the math, let's say it's a 1 in a million chance that someone who has very low risk, just randomly walking the street, has HIV. Even if a test is 99% predictive and accurate, there's only a 1 in 10,000 chance that that's right. Because it's 1% wrong out of a million. And that's 10,000. Only one of those 10,000 will be right. And when we look at tests, we always have to think about that. The test in the context. The ad absurdum arguments would be, an 80-year-old man who's been having, been very careful taking birth control pills. If he has a high beta HCG, that pregnancy test probably is a false positive. So you always have to think of the context. Just some definitions. Biomarkers are they're markers. Everything you get is a biomarker. It's a biologic specimen. But specifically here we're talking about prognostic biomarkers, which is a biomarker that somehow predicts or is linked to an outcome. Predictive biomarkers are for therapeutic treatments. They say, I can predict from that treatment the outcome. And then the more elusive endpoint is a surrogate biomarker, or a surrogate endpoint, which says that it's prognostic, it's predictive, but also that if I change that marker, I'll change the outcome. We do not have any predictive biomarkers. The FDA demands not only that it be predictive, the FDA demands that we have surrogate biomarkers. So in transplant, because we've gotten rid of acute rejection down to 10-15%, in a Bayesian world, it's almost impossible to have high positive predictive value with that. And because we don't have a surrogate endpoint for anything, almost all new immunosuppressive drug development has come to a halt. There's almost no development. The main focus of the Transplant Society now is how to change that paradigm. There are no new drugs being developed in transplant because we have no surrogate endpoints. So going back, in 1999, this was a Noonan Journal of Medicine by the Cornell group, by one of the most preeminent, brightest legends in our field. And no one could do this better. This was someone who is one of the fathers of transplant. And ROC curves mean yes, no. Is it a bird, is it a goose, or is it a plane? They came from World War II, and they didn't want to waste their missiles or their little bombs on geese. And when you looked on radar, you couldn't tell geese from planes. And so they came up with something called a receiver operating curve, which kind of was a binary endpoint. You go do it through logistic regression. Won't bore you with the details, but it kind of says yes, no. This is it or this is not it. A coin flip is 0.5. So anything above 0.5 means it's a little bit better than coin flip. Above 0.7 means it has some utility. So in this study, 0.86 is far better than a biopsy. That's about as accurate as you can get in discriminating yes, no, there's rejection there. That was in 1999. I'm sorry this slide looks small here, and just to go through then, since that time, this is just a sampling of NIH studies that have been done since we had the perfect biomarker. Everyone close their eyes as I figure the laser out. So it didn't matter. You could look at cytotoxic lymphocyte products. You could look at regulatory T-cell products. You could look at chemokines. You can combine them with down-regulatory proteins. You could look at injury molecules. You could look at chemokines. You could look at microRNA, sRNA, ELISpots, which are interferon gamma induced antigen-specific T cells. You could look for B cell, transitional B cells, transcripts, multidimensional platforms, 20 gene sets, 7 gene sets. You could sort the gene sets. It didn't even matter. You end up with the same number. You end up with a wonderful predictive value. You know what? There's still studies going on. And we're not using a single one. So why is that? Why are we still scratching our heads? Is everybody here wrong? Is it a problem in validation? So when you do biomarker research, there are 2 steps. There's discovery, and then there's validation. And you have to be very wary of discovery. Discovery, by definition, is always going to fit your molecules to your outcome. It's always going to look good. It's something called overfitting. So, by definition, you screen 1 million molecules, and you try to find the ones that fit best your endpoint. And that's part of discovery. So that's a necessary phase. The next phase, though, is validation. You have to validate that on a separate set. That's been a daunting project. You would think that would be easy. But at the NIH, in pharma, FDA, they all have different definitions of what is valid validation. Arguments break out. There's no agreement. I tried putting together a consensus statement on validation, and I called everyone, and everyone agreed, and then as the paper was being written, the 20 people who started ended up only being 4 people, because everybody else was offended by what other persons thought of validation was. So one question is, have we properly validated any of these? We've tried, and I think all of these have had validation studies. So I think there is an element that validation has been a problem, but I think there's a deeper problem about how we look at the immune system, and we'll get that into in a second. So this was a small little study we did years ago, kind of mind experiment. So again, our marker, well, we're asking the right question. So we were trying to predict acute rejection, with the idea that acute rejection, meaning your first response to that antigen, remember, an organ, that MHC, disparate MHC antigen sheds, is taken up like a virus. It's viewed as a virus would be viewed. It's viewed as an unwelcome inhabitant of our cells. And our immune system wants to get rid of it. And we presume that acute rejection, acute cellular rejection, T-cell mediated rejection, was the be-all and end-all. If we could get rid of that, grass would last forever. So to this day, that's become our endpoint. And so one problem with that being our surrogate, our endpoint, and trying to make that a surrogate, doesn't really fulfill the point that it's a surrogate. So that was the point of our study. We had done some animal experiments that said, you don't lose your graft to acute rejection. It has no effect. So we did the naturalistic experiment. Since all the drugs being developed were aimed at blocking the T-cell response of rejection, we took acute rejection from 1995 to 2000 down from 45% to less than 14%, around 14%. Over that same period of time, the risk of graft loss increased. Remember, a surrogate says, if I change that endpoint, I should change the outcome in the same direction. Amazingly, it changed it in the opposite direction. So are we asking the right question? Now, about predictions. This is another study we did. So in 1999, I keep picking on the New England Journal of Medicine. So anyone from Boston, please forgive me. It's just everything in the New England Journal of Medicine somehow becomes canonized. And for what it's worth, sometimes it doesn't hold up. So this was a study, in the white bars are a study from the New England Journal of Medicine. And essentially what it said was that from 1988 to 1995, we had doubled graft survival. And that was splashed, or editorials, people were celebrating in the street, everyone was patting themselves on the back. Transplant meetings were these huge hooray for us. And it was just, things were great, a chicken in every pot. The trouble was, the paper came out in 1999. And if you think about it, if you had data from 1995, by the time you really had 1995 to have survival, most of those people in those late cohorts only reached 3 years. So they were projections. They were predictions. So what we did is we waited until 8 years had passed, and we actually counted every vote. And we tried to avoid, we were in Chicago at the time, so we counted them even twice. And there was no difference in graft survival. And that's about as good as we are at predicting things. So any prediction you see, if people could truly predict, we can't even predict things we design. Trying to predict the natural world is really difficult, particularly when you deal with a complex system. And that was very sobering. The combination, and not because we wrote the paper, but the combination of those two papers reset people on an idea that we can't look at acute rejection anymore, and we haven't made progress. And so then a new paradigm became started about what are we supposed to be looking at. So what is acute rejection? Yes, I gave transplant grand rounds. I was embarrassed to even go through the slide, but I realized when I say acute rejection, it means something different to everyone. But the secret, so everyone in the audience feels better. When I say acute rejection, if you go to a transplant meeting of transplant immunologists, each one of them has a different definition and doesn't really know what it is. Or it's a very personalized definition. So I tend to think of acute rejection really as your first response, your immunologic response to that unwanted antigen, and not the way we tend to think of. People define it in different ways. That you have to have this much interstitial inflammation, you have to have this much inflammation in the vessel, or that. It's simply your body attacking the organ that you've transplanted because it sees that it has shed an unwanted protein, and that protein is harboring in that organ. And we don't want that to spread somewhere else. So basically, an antigen is taken up by antigen-presenting cells. That MHC antigen, the HLA molecule, is taken up by an antigen-presenting cell. That antigen-presenting cell then presents it to T cells, and those T cells see self, and they see non-self. So they say, that's me, and I really only care about me. No, that's me, And in me is something that I don't want. That's not me. I've never seen that before. If I've never seen it before, it's probably something I should get rid of. So a response is set up. T cells get activated, they hone in to the source, and they form a compartment around it, an inflammatory compartment. And that's what we call acute rejection. The trouble with that is, that happens to us all the time. It's pretty nonspecific. It happens with an unwanted antigen, but we sometimes forget that injury even begets inflammation. And that'll look just like rejection. If you cut your finger, it gets red and swollen, right? It gets inflamed. That's an immunologic reaction to injury. But what happens to you after that? Does your finger fall off? It gets better. Because our immune system is balanced. For every upregulatory protein, there's a downregulatory protein. We get inflammation, and then usually it goes away without us intervening. We get the flu, we get a cold, and it goes away. Now the trouble with a transplant is that a lot of times when things go away, the injury or the antigen goes away. The trouble with the transplant is you're stuck with that antigen. And you're lucky to be stuck with that antigen. We don't want you to, get rid of that antigen. So the trouble with transplant is that antigen never goes away. That virus you can't clear. And if you do clear, you kill the host. And that's not good for anyone. So it becomes kind of complex. I'm not going to bore you with this, but the only reason I'm mentioning this is these are a series of experiments that I was fortunate to take part in with a gentleman named Phil Halloran, who is probably the most brilliant immunologist that we've had over the last 20 years, and taught us a lot about transplant. So what these experiments were, is T-cell rejection, the initial response, stereotypical? And it turns out it is. The initial response is stereotypical and predictable. That what we see is, these were in mouse models, you kind of sacrifice the mouse and you look. And so both transcripts, histology were done, affymetric chips were done, all sorts of tests were done to look at what's the mechanism. So at first, on day one, when you see that antigen, immediately interferon gamma is mobilized. And interferon gamma immediately starts a cascade of events. Solute transporters, energy-dependent ATPases are downregulated right away before you ever see a T cell. Cytotoxic T cells are activated. And there's a direct effect on paracellular pathways. But the histology is not changed. It's clean. There's no rejection there. But it started. And that organ's not working right. Even before the inflammation, you can see that inflammation. On day 3, a T cell compartment in that kidney is formed in the epithelium. There's an increase in those cytotoxic lymphocytes, those killer T cells, as they used to be called, and an increase in injury transcripts occur. But by day 10, what you start seeing are counter-regulatory proteins. IL-10, PD-1, CTLA, they get upregulated. And by day 27, there's a mix, and it kind of goes away. And that is a very stereotypical response. That's probably the initial response. But that doesn't injure your graft. That doesn't cause graft loss. So the question is, what are the mechanisms that cause graft loss? So like I said, in T-cell rejection, that initial response doesn't work. The pathogen's still there, the invader is still there, the antigen is still there. It didn't work. So the immune system's kind of smart. So it's probably not going to do the same thing again for something that didn't work. So it's going to try different mechanisms to get rid of that antigen. So other parts of the immune system are mobilized. And then we start getting into the complexity of the system. Remember, the immune system evolved to deal with millions of unknown pathogens, and then another million of potential unknown pathogens that mutate over hours. So it has to have an enormous degree of complexity and plasticity. And I'll make a case at the end that it may be random. Because if I were fighting that way, the most parsimonious mathematic way to deal with that many unknown invaders and potential invaders is to have a random system. But I know you won't believe it at the end, but I'll try to convince you that maybe that's a possibility. So in late graft loss, deep memory is engaged. We now start remembering that antigen. And when we remember it, that's a bad thing. Because when we remember it, we know it's there. So when it comes up, we're mobilized. We have a strategy for it. It's not like a new thing we weren't expecting. We know it's there. So we're going to mobilize different arms of the immune system. And I'm not going into too much detail. There are so many proteins and there's so much crosstalk in the immune system that any one molecule can be inflammatory, anti-inflammatory, depending on when it occurs, what's in its vicinity, what other molecules are there with it. I won't bore you with the mind-boggling details of it, but the system is a true system. It's not an isolated molecule. Every molecule is dependent on what's happening around it and when it happens, in the context of which it happens. As I said, when that deep memory is engaged, all the complexity starts. Now here's another problem. Aside from being complex, when we look at injuries that cause the loss of an organ or death, by definition, they are rare events. You're not allowed to get too many events that could kill you. I grew up on like Bugs Bunny, and then now I still watch Family Guy, but Wile E. Coyote and Bugs get into that fight about who's the better magician. And they go back and forth. And, Wile E. Coyote had a contract with Acme Dynamite. And so the last trick was Wile E. Coyote, sets himself up and dynamite goes off. You see Wile E., ascend to heaven. And Bugs says, you win, you can be the magician. Wile E. Coyote says, well, trouble with that trick is I can only do it once. And the problem is that with things that cause graft loss, you can only do it once. So by definition, it's rare. And the timing is unpredictable. You don't know when. If we knew when, we could prevent it. So by definition, that rare event has to be unpredictable. So how do you predict something that's by nature unpredictable and rare? If you know the answer to that, please contact Janet Yellen right now. Because I want to retire in safety. So, we're at war with that pathogen. So people have thought of ways. So there's something called game theory. So again, one of my heroes is, well, not one of my heroes, but I have too many heroes. I need to get a life. So one of my heroes is John von Neumann. And I don't know how many people, raise your hand if anyone's ever heard of John von Neumann. See, that's when you go to a really smart place. People hear of people. Oh, wow, you just ruined my... So John von Neumann was a brilliant mathematician. And he wasn't maybe he was one of the best, but he's certainly the fastest mathematician. So if you had a problem, you went to John von Neumann. And he had a really restless mind. So he went everything from economics to the quantum physics to social interactions to computers. The mathematics for binary code come from John von Neumann. And he's affected our life probably as much as anybody has. And the thunder's been ruined that everybody doesn't know him. One of the things he came up with was the idea of game theory. That when we are dealing with another entity, there's a game going on. And being a mathematician, he looked at, in that game, how does one maximize the probability of being successful? And as people started thinking of complex systems, the idea that perhaps these systems are smart, so they're going to maximize the probability of success. So a whole field came up of trying to explain these phenomena through game theory, of what would maximize the ability to get rid of that antigen and not hurt yourself. And in that game, and what also would be okay with that antigen. Now, the trouble with von Neumann and Morgenstern, who we did it with, was they assumed that everybody liked each other. And they were all going for the greater good. And then about a dozen years later, Ron Howard made a movie. No, I think he came before that. I don't know. I get mixed up sometimes. But anyway, Nash came along. And Nash said, well, actually, if you're having a war, probably people aren't really getting along. And making the assumption that everyone's out for the best good is probably not maybe the right thing. So maybe it's a non-cooperative game. And thus the idea of a Nash equilibrium, where not everyone is satisfied, but the worst doesn't happen, and the aggregate probability between the two, the aggregate probability for each one is maximized. I won't bore you with it all, but it's tried to be explained that way. And maybe that's so. But some of the tenets don't really make sense, because one of them is that to be in a Nash equilibrium, each side has to know the probabilities of success. And each side has to make a presumption that their strategy is independent of what the other entity does. So I'm not sure we can explain these phenomena by game theory, because I'm not sure it really is a game. And I'm pretty sure we don't inherently know the probabilities of success. So what else could be going on? Are these events just rare? Is this a Bayesian problem? Does it take... Because we do have a number of tests that can rule out things. But as I mentioned, it's not hard to rule out things that happen rarely. If you're trying to rule out prostate cancer in, a 50-year-old woman who has no problems urinating, then probably a coin flip is going to have 100% negative predictive value. So ruling out things for rare events is not hard. Ruling them in becomes impossible when the events get below 10%. So could it be that we're just looking at rare events? And we have to use some kind of different way of looking at it. There is a field of rare event mathematics. Maybe we have to look at it as rare event mathematics. The events occur in unpredictable time frames. So are we testing at the right time? Does the immune system work on the Roman calendar? Does the immune system, have a clock and say it's 8 a.m.? We tell people you have to be in the lab at 7:30. If you're there at 8:30, it's no good. You have to be there at 7:30. You have to be fasting. All these things we tell them. I'm not sure the immune system really, it probably sleeps in late lots of days and doesn't keep much time, hangs out, And I don't think it knows month it is or week it is, but we make our tests. We say, okay, we'll get that test on month 1 and month 3, and we'll get it at 8 a.m. So why do we think that we're going to catch that phenomenon when it's starting, when we're trying to predict it before it happens? So could it be just that, the time-space continuum is different for the immune system than our artificial idea of time? To get a little metaphysical at 8:15, which I'm sure you all love. Is it just too much complexity in the immune system? Is it so complex that simple, analysis like ROC curves and linear regressions, min-max, random forests, machine learning, all the things we think are fancy, maybe they're not up to the task yet? Could that be it? I misspelled this and got chastised yesterday. But one of your faculty members, a relative of his, described complex systems as geometric and as fractal, meaning that they kept the same shape but changed size. And should we be looking at the system in geometric ways? In other words, if you go onto Google, I'm amazed at Google, even though it's now Alphabet. They still call it Google. In Google, you can put a face on Google. And there's 6 billion faces in the world, I think. I haven't counted all of them, but you put a face on. Now, everybody has 2 eyes and 1 nose and a mouth and 2 ears. Some people have hair, some of us don't. And amazingly, you'll get that one person. And that's all geometry. We all have a unique, if you add up the unique angles that make up a face, that's all geometry. So could we be describing it as the shape of the data instead of our usual way of saying, this predicts this with a C statistic or an odds ratio or a positive predictive value? Should we start looking at, again, Mandelbrot sets and other ways of looking at it? It's an upregulatory system. So if we do it and we do geometry, we'll have to do non-Euclidean geometry. The parallel lines will meet because it doesn't mean the more molecule you have, the more response you have. As you get more molecules, it does go to a point. And then it turns out that after a while, the more you get, the less response you get. And the parallel lines meet. And so do you need to use some kind of non-Euclidean geometry? Euclidean geometry, standard, parallel lines never meet. But non-Euclidean is kind of spooky. I'm asking those questions because I'm hoping you'll have the answer, because I don't have the answer. Or is the immune system strictly stochastic? Is it built that way? Is it meant for us to not be able to unlock the key? Because if we can pick that lock, then maybe Mother Nature will be able to pick that lock. And Mother Nature is a lot smarter than us. So would we want a predictable system? Would we want to be found out? Or, in evolutionary terms, the most parsimonious response to a complex world is to be random. And so if no one asked me to build us, but if someone asked me to build us, I would make our immune system random. Because there's enormous power in randomness. In physical sciences, we accept randomness. I spooked out our CEO of our hospital the first time I met him. He's a scary guy. But I guess I was happy at Mayo Clinic, so I was okay not taking the job. So I went, and I kept doing that. And he first thought maybe I always had Asperger's, and he wanted to hire me because he thought I could have a beautiful mind or something. And he kept doing that. I said, Glenn, you ever wonder why your hand never goes through this? when the essential nature of it is 99.99% space? And the reason it doesn't go through is because there are electrons jumping randomly. And within that randomness is tremendous stability and strength. And I didn't hear from them for 3 months. But I think he got fired and someone else came in and they didn't remember that meeting. But anyway, in physical sciences, randomness is well recognized as being part of the repertoire of life. We don't like that. We're doctors. We go see a patient. We like a story. Richard Thaler just won the Nobel Prize in economics. And he followed Daniel Kahneman and Amos Tversky. And the power of narrative, the power of thinking we know, confirmation bias, all those things are hardwired in us. We don't like randomness. We don't like not knowing. In that vacuum, we will find ways to be able to justify reasons why it's not that way. And it's just hardwired on us. The power of a stochastic system is it doesn't take a lot of molecules to have complexity. In order to deal, let's say there are 1 million pathogens mutating daily, you would need 1 million molecules to deal with that if it were predictable. In a random system, the mathematics become very simple. You need very few molecules to deal with almost infinite complexity. So it might make sense that it's a random system. I don't know. If I knew, it wouldn't be random. It's a short talk, but again, 2 people, I think everyone here in the audience is smarter than me, but another 2 people who are much smarter than me used to have a fight with each other. Some guy named Einstein and some guy named Bohr. And they had tremendous respect for each other. And even though Einstein was the father of quantum physics, his thesis, PhD thesis, was on Brownian motion. He made the mathematics for random motion. But, and then Niels Bohr is, the father of quantum physics. He took that and expanded on it and was a thoughtful man, a follower of Kierkegaard, comfortable with ambiguity. So they had a long-running, very cordial feud. And I wish medicine would have those kinds of talks. We tend to get angry at each other if someone challenges us. And Einstein would always challenge Bohr, but they still respected each other, immensely respected each other. They just disagreed. And Einstein would monthly send Bohr mind experiments trying to disprove quantum physics, because at the heart of quantum physics was randomness. And he'd be thwarted. Bohr every time would come up with an explanation, and then he would come up with another thing. And finally Einstein just got fed up trying to do it. And he said, and everyone, I think most people remember this quote, and there were famous letters, there's books written on the letters back and forth. So Einstein finally fed up with trying to disprove what he knew. Couldn't be. Told Bohr, Bohr, I can't accept that the universe is purely random. Because God would never play dice with the universe. And everyone remembers that quote. And the last letter, though, was Bohr's response to Einstein. And it was a very short, simple sentence. Einstein, can you stop telling God what to do? I think, going forward, I think if we're going to make progress in this area, in complex systems, a lot of humility is going to have to take place. But more importantly, the lessons learned, a lot of cooperativity and respect for other points of views and openness to looking at these questions is going to be the key. We may not get the right answer, but I think the adversarial nature, I've been editor of journals for years, and the rancor that occurs when someone disagrees with another person is really disheartening. I think we have to accept that we can disagree, and within that disagreement becomes miracles of discovery. That real discovery comes from disagreement, and we have to learn to have civil disagreements and listen to each other. And if anything else, because there are obviously residents here, and who am I to say anything? But I think if there's anything to learn is welcome disagreement, welcome oddball ideas. Because, they may or may not be right. But together, your idea and their idea, you'll be incredibly powerful. And avoid disagreements that are personal or filled with emotion. We're all trying to do the same thing. If we're doctors, we're trying to make patients' lives better. We're all in it together. And again, like the Manhattan Project, if we do it together, I have no doubt we'll solve this problem. I know my lonely little brain can't figure this out, but if people disagree with me enough and we have discussions, maybe it will. And I'll mercifully end there and really thank you for your attention.
Well, thank you, Bruce, for this uplifting talk. I would ask you guys to ask questions, and please repeat the question. Okay, I will start with one question. In terms of the value of these biomarkers and the way we are thinking about the timing of measurement and monitoring, etc., what are your thoughts about real time? Let's say we have unlimited funding and time. What are your thoughts about real time?
Do I get superpowers too?
Exactly.
Can I fly and see through lead and other things?
We do.
Okay.
So what are your thoughts about real-time monitoring? Let's say you have a watch that monitors your T lymphocytes from the time you get a kidney transplant till the time that transplant is dead, and you do that in 1,000 patients, just without any major intervention, but monitoring of the whole biological process as much as possible to better understand what is going on there.
So this is an example of what I'm talking about. I love Aji. So I know I can tell him. I think that would be the worst idea possible. And the reason is, we already have too much information. And my question back to Aji is, what will we do with it? We don't have the analytics. And now we have even more information. And we'll make up stories about it, and we may veer way off course. So I might throw back at Aji that maybe we need to think beforehand, what are we going to do with that data before we get the data? We have it almost backwards. We get the data, and then we try to make sense. And we think that's really the virtuous way to do it. And maybe we should think first about what are we going to do with this data? In clinical medicine, you do that, right? You don't randomly get ultrasounds every day and think, well, fine. You have a suspicion, and you get it, and I'm sure you tell every one of your fellows, don't get that test unless you know what you're going to do with it. So I respectfully disagree and say, I wouldn't want to do that because I wouldn't know what to do with it. And I'd like to sit down and figure out what I'd like to do with it before embarking on that. I just lost my best friend.
Other questions for Bruce? Well, thank you very much.